Welcome to Lecture 4 of our flow matching tutorial. This is the main event. Over the past lectures, we built up the foundations piece by piece. In Lecture 1, we developed the intuition. Generative models transform noise into data using velocity fields. In Lecture 2, we learned how neural ODEs let a network define a velocity field and how flows transport distributions. In Lecture 3, we designed probability paths, the conditional paths that guide individual particles from noise to specific data points. And in Lecture 3b, we built the mathematical toolkit, expectations, conditional expectations, and the key gradient linearity property of the MSE loss. Now we are ready for the main question. How do we actually train the neural network? How do we learn the velocity field without solving expensive ODEs at every training step? Today, we answer that question with the flow matching algorithm. We will see the loss function, the mathematical trick that makes it tractable, the actual code, and the practical extensions that make it work at scale. By the end of this lecture, you will understand the complete recipe for training and sampling with flow matching. Let us quickly recap where we are. Over lectures 1 through 3b, we built a complete picture of the flow matching setup, including the mathematical tools we need, except for the training algorithm itself. We know that a velocity field ut of x generates a probability path pt, which transforms a source distribution p into a target distribution q. We know how to build conditional probability paths. For each data point x1, we define a simple path that brings noise to that specific data point. For the linear path, the conditional velocity is just the direction from noise to data, x1 minus x0. We also know that the marginal velocity field, the one we actually want to learn, is the conditional expectation of these conditional velocities. It averages over all possible data points that a particle at position x at time t could be heading towards. Here is the problem. Computing this marginal velocity requires integrating over the entire training dataset. For every point x, you would need to check every single data point x1 and weight its contribution. That is completely intractable. You cannot evaluate this integral, let alone differentiate through it. In Lecture 3b, we built the mathematical toolkit for what comes next. We saw that MSE gradient linearity means training against individual targets gives the same gradients as training against their average. That property is exactly what will let us bypass the intractable integral. So the question becomes, can we train our network to match the marginal velocity without ever computing it? The answer is yes, and that is the flow matching algorithm. Let us write down the ideal loss function for flow matching. If we could compute the true marginal velocity, ut of x, training would be straightforward. Just do regression. The flow matching loss is an expected squared error. Sample a random time t uniformly between 0 and 1. Sample a random point xt from the probability path at that time. Then measure how far our network's prediction is from the true velocity. In other words, it is just mean squared error between our prediction and the target, averaged over time and space. This is conceptually simple. If we could minimize this loss to 0, our network would perfectly reproduce the marginal velocity field, and solving the ODE at inference time would generate exact samples from the target distribution Q. But here is the catch, and it is a serious one. The true marginal velocity ut of x requires a conditional expectation that integrates over all data points. For each position x at time t, you need to consider every possible target x1 in your dataset and weight its conditional velocity by the posterior probability of that target given x. This integral is intractable for any realistic dataset. So we need a workaround. And this is where the key insight of flow matching comes in, is we can replace this intractable loss with a tractable one that uses only conditional velocities, and the two losses produce exactly the same gradients. Here is the conditional flow matching loss, and this is really the core formula of the entire course. Instead of regressing onto the intractable marginal velocity, we regress onto the conditional velocity. The procedure is sample a time t, sample a noise point x0 from p, sample a data point x1 from q, compute the interpolated point xt, using the conditional flow psi t, and then train the network to predict the time derivative of that conditional flow. For the linear optimal transport path, which is the most common choice, this becomes incredibly simple. xt is just the linear interpolation, 1 minus t times x0 plus t times x1, and the target velocity is just x1 minus x0, the direction from noise to data. So each training step is literally sample noise, sample data, interpolate, and do regression. No ODEs anywhere. This is why flow matching is revolutionary. Compare this to neural ODE training, where each gradient step required solving a full ODE forward and then another ODE backward for the gradients. That was 50 to 200 times more expensive. Here, a single training step is one forward pass through the network and one backward pass. It is as simple as training any regression model. But the critical mathematical question remains: why is this valid? The conditional FM loss uses conditional velocities, not the marginal velocity. How can we be sure that minimizing this loss gives us the right marginal velocity field? The answer is stated at the bottom of this slide. The gradients of the two losses are identical. Every gradient descent step you take on the conditional loss is exactly the same as a gradient descent step on the ideal marginal loss. This is the marginalization trick, and it is what we will prove next. This is the marginalization trick, which is Theorem 3 in the tutorial paper. It is the mathematical backbone of the entire flow matching framework. The theorem says, if you have a collection of conditional velocity fields, each of which generates its own conditional probability path, then the marginal velocity field, defined by averaging these conditional velocities, automatically generates the marginal probability path. Let me break down what this means concretely. For each data point x1, we define a conditional path that brings noise to x1, and a conditional velocity that drives particles along that path. The conditional velocity for each individual data point is trivially easy to compute. The marginal velocity, which is what we actually want, is the average over all data points, weighted by the posterior probability of each data point given the current position. Theorem 3 guarantees that this average velocity field is itself a valid generating velocity for the marginal path. The conditional paths combine correctly at the marginal level. You do not need to check anything extra. As long as the individual conditional paths are valid and the regularity conditions are met, the marginal path is automatically valid. The conditions are mild. The conditional paths need to be smooth, the target distribution Q should have bounded support, and the marginal density Pt of x should be positive for all x and t in the interval 0 to 1 excluding t equals 1. These are satisfied by essentially all practical choices of paths. An important generalization noted by Tong and colleagues is that the conditioning variable does not have to be x1. You can condition on any variable z, the source x0, the pair of source and target, or something else entirely. The theorem holds in full generality. Let me now sketch the proof of why the two losses have the same gradients. This is an elegant argument that relies on a single algebraic property of the loss function. Start with the gradient of the ideal flow matching loss. This involves the marginal velocity ut of x, which we know is the conditional expectation of ut of xt given x1, conditioned on xt equals x. So we have the gradient of the squared difference between our prediction and a conditional expectation. Now here is the key step. This is exactly the gradient linearity property we proved in lecture 3b. For the mean squared error, the gradient with respect to the second argument, that is, with respect to v in the expression norm of u minus v squared, is simply minus 2 times u minus v. This is linear in u. And because it is linear in u, the expectation over u can be pulled inside the gradient. In other words, the gradient of the MSE with respect to v evaluated at the expected value of y is the same as the expected value of the gradient evaluated at each individual y. The expectation commutes with the gradient. This means we can replace the intractable conditional expectation inside the loss with the individual conditional velocities, and the gradient does not change. After pulling the expectation inside, we can use Bayes' rule to rewrite the outer expectation over xt with the inner conditional over x1 given xt as a joint expectation over x1 from q and xt from the conditional path. This gives us exactly the gradient of the conditional flow matching loss. This property is not specific to MSE. It holds for any Bregman divergence, which is a family of loss functions that includes MSE, KL divergence, and many others. The gradient of a Bregman divergence with respect to its second argument is always affine in the first argument, which is exactly what we need for the expectation to pass through. The consequence is powerful. The global minimizer of the conditional FM loss is exactly the marginal velocity field. Even though we train with conditional targets, we converge to the marginal. Let us now look at the actual code. This is adapted from listing 1 of the tutorial paper, and it implements the complete flow matching training algorithm from scratch. First, we define the velocity model. It is a simple, feed-forward neural network that takes as input the concatenation of the current position xt and the time t and outputs a velocity vector. In this 2D example, we use 3 hidden layers with ELU activations. Nothing fancy. Now look at the training loop. This is where the magic of flow matching becomes apparent. Each iteration has 5 key lines. Line 1, sample target data x1 from the 2 moons dataset. This is our target distribution Q. Line 2, sample noise x0 from a standard Gaussian. This is our source distribution P. Line 3, sample a random time t uniformly between 0 and 1. Line 4, compute the interpolated point xt equals 1 minus t times x0 plus t times x1. This is our position along the linear conditional path. Line 5, compute the target velocity dxt equals x1 minus x0. This is the conditional velocity for the linear path. Then we compute the MSE loss between our network's prediction and the target velocity, and backpropagate. That is it. No ODE solving, no expensive simulation, no adjoint method. Just sample, interpolate, regress, update. Compare this to the neural ODE training from Lecture 2, where you had to solve a full OEE at every training step, then backpropagate through the solver. Flow matching reduces all of that to a standard regression training loop. This simplicity is exactly why it has become the dominant approach for training generative flow models. So far, we have trained the network to directly predict the velocity. But for affine paths, the marginal velocity can be decomposed in different ways, and this gives us 3 equivalent parameterizations to choose from. The first is velocity prediction, which is what we have been doing. The network directly outputs ut of x. The training target is alpha.t times x1 plus sigma.t times x0. For the linear OT path where alpha t equals t and sigma t equals 1 minus t, this simplifies to x1 minus x0 as we saw. The second is data prediction, or x1 prediction. Here the network predicts the clean data point x1 that the particle is heading towards. You can think of this as a denoiser. Given a noisy sample, xt, at time t, predict the clean data. Once you have the x1 prediction, you convert it to a velocity using a simple formula involving the scheduler coefficients. The third is noise prediction, or x0 prediction, also called epsilon prediction in the diffusion literature. The network predicts the noise x0 that was used to construct xt. Again, there is a conversion formula to go from noise prediction to velocity. All 3 parameterizations are mathematically equivalent. They lead to the same marginal velocity field, and you can convert between any 2 using simple algebra. The conversion table in the paper gives all the formulas. In practice, the choice of parameterization can affect training dynamics, and different applications favor different choices. Data prediction tends to work well in practice, which is one reason why Stable Diffusion 3 and FLUX use the x1 prediction parameterization. Let us look more carefully at the practical implications of choosing a parameterization, because there are some subtleties that matter in real implementations. The issue is singularities at the time boundaries. For x1 prediction, the conversion formula from data prediction to velocity involves dividing by sigma t, which goes to 0 as t approaches 1. For x0 prediction, the formula involves dividing by alpha t, which goes to 0 as t approaches 0. In theory, these singularities cancel. As sigma t goes to 0, the model's x1 prediction should become more and more accurate, compensating exactly for the diverging coefficient. The product remains finite. But in practice, the learned model is never perfect, and even small errors in the prediction get amplified by the diverging coefficient, leading to numerical issues. The practical solution is to be aware of which boundary is problematic for your chosen parameterization. x1 prediction is stable near t equals 0, but potentially unstable near t equals 1. x0 prediction has the opposite behavior. Direct velocity prediction avoids this issue entirely, but may have other trade-offs in training dynamics. An elegant consequence of the conversion formulas is that you can train with one parameterization and deploy with another. For example, you might train with x1 prediction because it is stable and has nice gradient properties, then convert to velocity at inference time. You can even change the scheduler post-training. The paper shows how to transform a model trained with a variance-preserving schedule into one that uses the conditional OT schedule for sampling. This is possible because all affine schedulers with the same signal-to-noise ratio profile produce the same samples in theory. Once training is complete, we have a neural network, ut theta of x, that approximates the marginal velocity field. To generate samples, we solve the ODBN defined by this learned velocity. The procedure is: start from a random noise point, x0, sampled from the source distribution, typically a standard Gaussian. Then integrate the ODE from t equals 0 to t equals 1 using the learned velocity field. The endpoint x1 is our generated sample. The simplest solver is the Euler method, which we covered in Lecture 2. Divide the time interval into n steps of size h equals 1 over n. At each step, evaluate the network to get the velocity, then take a step in that direction. The more steps you take, the more accurate the solution, but the slower the generation. For the linear conditional OT path, the true trajectories are very close to straight lines. This means the Euler method with very few steps can already give good results. In fact, if the paths were perfectly straight, a single Euler step would give you exact samples. In practice, the marginal velocity field is not perfectly linear, so you need some steps. But the near straightness means you can get away with far fewer steps than diffusion models typically require. Higher-order solvers like the midpoint method give much better accuracy per step at the cost of more network evaluations. The midpoint method evaluates the network at the current position to get an estimate of the halfway point, then evaluates the network again at that halfway point to get a better velocity estimate. Each step costs 2 network evaluations instead of 1, but the error decreases much faster. In production systems, 8 to 100 steps with the midpoint or Runge-Kutta solver is typical. The flow matching library provides all of these solvers ready to use. Here is the sampling code, shown in 2 versions. On the left, the from-scratch implementation that continues our training code from listing 1. On the right, the clean version using the flow matching library. The from-scratch version makes the algorithm transparent. We start with 300 random noise points. We define 8 time steps between 0 and 1. Then we loop through the time steps, and at each step we apply the midpoint method. Evaluate the velocity at the current position, take a half step, evaluate the velocity again at the midpoint, then take the full step using the midpoint velocity. After 8 steps, our noise points have been transported to approximate samples from the data distribution. The library version on the right is more concise. You create an ODE solver, give it your trained velocity model, and call solver.sample with the initial condition and solver parameters. Under the hood, it does the same thing, but the library handles edge cases, different solver methods, and batching for you. Notice the asymmetry between training and sampling. During training, we never solve an ODE. Each training step is just one forward pass and one backward pass. During sampling, we do solve an ODE, but only once, and only in the forward direction. There is no backpropagation through the solver at sampling time. This is fundamentally different from neural ODE training, where you had to solve ODEs in both directions during training itself. With 8 steps on our 2D moons example, you get recognizable moons. With more steps, the quality improves. For production image generation, 20 to 100 steps is common. In many applications, we do not just want to generate random samples. We want to generate samples conditioned on some guidance signal. Given a class label, generate an image of that class. Given a text description, generate a matching image. Given a low-resolution image, generate a high-resolution version. The flow matching framework extends naturally to conditional generation. The key idea is simple. Instead of sampling data points x1 uniformly from the full data distribution Q, we sample them from the conditional distribution Q of x1 given y. Everything else stays the same. The conditional path pt given 1 does not depend on the guidance variable y. Only the mixture weights change. The guided velocity field is the conditional expectation of the conditional velocity, but now conditioned on both x, t, and the guidance variable y. This velocity generates a guided probability path that starts at the same noise distribution p and ends at the conditional target q of x1 given y. In practice, the training loss looks almost identical to the unconditional case. The only difference is that the network now takes the guidance variable y as an additional input alongside xt and t, and we train it to predict the same conditional velocity target. The guidance variable can be anything: a class label, a text embedding, a low-resolution image, or an audio clip. This approach works well when many data points share the same guidance signal, such as class-conditional generation with a few hundred classes. But when the guidance variable is complex and non-repeating, such as unique text captions, you need additional techniques to make the conditioning effective. This brings us to classifier-free guidance. Classifier-free guidance, or CFG, is the practical trick that makes conditional generation work well in large-scale systems. It is used in virtually every modern text-to-image model, including Stable Diffusion 3, FLUX, and MovieGen. The idea comes from a Bayesian decomposition. By Bayes' rule, the conditional score, which is the gradient of log pt given y, can be written as the unconditional score plus the gradient of a classifier that predicts y from x. Instead of training a separate classifier, the insight of Ho and Salamens is that you can estimate this classifier implicitly as the difference between the conditional and unconditional scores. In practice, this means training a single model that handles both conditional and unconditional generation. During training, you randomly drop the conditioning signal y with some probability, replacing it with a null token. This teaches the network to generate both with and without guidance. At inference time, you run the network twice at each step, once with the condition y and once without. Then you combine the two outputs using a guidance weight w. The formula is 1 minus w times the unconditional velocity plus w times the conditional velocity. When w equals 1, you get the standard conditional model. When w is greater than 1, you amplify the guidance, making the generation more faithful to the condition, but potentially less diverse. Values of w between 3 and 7 are typical in practice. The guidance weight gives you a dial to trade off between diversity and fidelity. At low w, you get diverse but loosely conditioned samples. At high w, you get samples that are very faithful to the condition but less varied. This trade-off is fundamental, and CFG gives you direct control over it at inference time, without retraining. It is worth noting that the exact distribution sampled by CFG is not fully understood theoretically, but empirically, it works remarkably well and has become the standard approach. The coupling between source and target samples is another degree of freedom in the flow matching recipe, and it has important practical consequences. First, paired data couplings. So far, we have assumed independent coupling. x0 is random noise sampled independently of x1, but many tasks naturally have paired data. In image inpainting, the source is a masked image and the target is the filled image. In super resolution, the source is a low-resolution image and the target is the high-resolution version. For these tasks, you use a dependent coupling. You start with clean data x1 from Q, then apply a degradation to produce x0. The flow model then learns to undo the degradation. The beautiful thing is that the training algorithm is completely unchanged. You just swap the data loader. Second, mini-batch optimal transport couplings. Even in the standard noise-to-data setting, the pairing between noise points and data points matters. With independent coupling, nearby noise points might get paired with distant data points, producing crossing paths. Mini-batch OT fixes this by solving a small optimal transport problem within each mini-batch to find the cost-minimizing pairing. Let us see what this looks like visually. Here's the difference visually. On the left, independent coupling. Noise points are randomly paired with data points regardless of proximity. The resulting paths cross each other, which makes the velocity field complex and hard to learn. A complex velocity field means you need many ODE steps at inference to get good samples. On the right, mini-batch OT coupling. We solve a small optimal transport problem within the mini-batch to find the pairing that minimizes total transport cost. Nearby noise points get paired with nearby data points. The paths are straighter and do not cross, which produces a simpler velocity field. A simpler velocity field means fewer ODE steps at inference. The method is straightforward. Sample k noise points and k data points, solve the k by k assignment problem using a linear program, and train with the optimal pairs. As k grows, the paths approach the true optimal transport solution. In practice, k equals the mini-batch size, which is usually enough to see significant improvements in sample quality and inference speed. Let us step back and see the complete flow matching recipe side by side. The training side is remarkably simple. Sample a time, a noise point, and a data point. Compute the interpolation along the conditional path. Compute the MSE between the network's velocity prediction and the conditional velocity target. Backpropagate and update. Repeat. No OD solving, no expensive simulation, no adjoint method. The sampling side requires solving the learned ODE from t equals 0 to t equals 1. Start from noise, step through time using the learned velocity field, and arrive at a sample from the target distribution. Higher order solvers and more steps give better quality. The mathematical foundation connecting these two sides is the marginalization trick, Theorem 3. It guarantees that training with easy conditional velocities produces the correct marginal velocity field. The proof relies on the affine invariance of Bregman divergence gradients, which allows expectations to pass through the loss gradient. No ODE solving during training. No marginal computation. Just regression. Let us take stock of what we accomplished today. We now have the complete theoretical foundation for flow matching. We derived the flow matching loss and its conditional counterpart, the CFM loss. We proved, via the marginalization trick, that training with easy conditional velocities gives us the correct marginal velocity field without ever computing it directly. The proof relies on a beautiful property of Bregman divergences. Expectations pass through the loss gradient. We wrote the training loop in just a few lines of code. Sample noise, sample data. Interpolate, predict the velocity, compute MSE. That is it. No OD solving during training. We also wrote the sampling code. Solve the learned OD from noise to data using Euler or higher order solvers. We covered velocity parameterizations, which give flexibility in what the network predicts, velocity directly, clean data, or noise. We saw conditional generation with classifier-free guidance, the dominant technique in modern text-to-image systems. And we explored data couplings and mini-batch optimal transport for straighter trajectories. In Lecture 5, we shift from theory to practice. We will do a full code walkthrough on the 2 moons dataset, discuss architecture choices like UNets and diffusion transformers, and see how flow matching scales to images, video, and even protein structures. We will take everything we built today and turn it into a working system. Thank you for following along. The elegance of flow matching is that it reduces a hard problem, learning a generating velocity field, to simple regression. That simplicity is what makes it scale. See you in Lecture 5.